Well, it's time to play a bit with these spacetime diagrams. Han Solo and his crew are escaping Kessel with coaxium, a rare fuel necessary to travel in hyperspace. The Millennium Falcon flies at 60% of the speed of light, away from Kessel. To represent the world lines of the Falcon traveling at 0.6 c, we draw a line where the tangent is precisely that, c squares to the right and 5 squares up. Event A indicates their departure from Kessel. After 5 seconds, measured from Kessel, they fire a phaser blast to the Falcon. Event B. The phaser travels at the speed of light, so 1 square to the right and 1 square up indicates its trajectory. At that same time as measured from Kessel, Han drops a fuel tank behind, setting the tank at rest relative to Kessel, while the Falcon continues on ahead of it. That is event C. Event D indicates the moment where the phaser blast hits and destroys the tank. First, let's calibrate the axis. Because beta is 0.6, that gives us a gamma of 1.25. So for every 5 seconds in Kessel, there are 4 seconds in Falcon. The time interval between A and C as measured from Kessel is 5 seconds, so that time interval as measured from the Falcon has to be 4 seconds. Event D is the explosion of the fuel tank. As seen from Kessel, it takes place at 8 seconds, but as seen from the Falcon, we need to draw a line parallel to X' axis and see where it crosses the CT' axis. Event Q is the explosion of a meteor that collides with Kessel's protective shield. According to the measurements in the Falcon's frame, this event occurs at T' equals to 3 seconds and X' equals to 2 light seconds. In order to locate this event in the spacetime diagram, we draw lines parallel to X' and T' that cross 3 and 2. This, as measured from Kessel, occurs at distance a bit shorter than 5 light seconds and at a time at about 5.5 seconds. But after doing this with the spacetime diagrams, let's do the calculation with Lorentz equations, just to see if everything agrees, if what we find with Lorentz equation is the same as what we found with these Minkowski spacetime diagrams. So first I want to calculate what are the coordinates of that explosion D as seen from the Millennium Falcon. As seen from Kessel, using those units where the distance we measure that in seconds or in light seconds, the distance that light travels in that amount of time, and takes place at 3 seconds and at a time of 8 seconds, so this is the distance, that is the position. I'm going to use Lorentz transformation equations to find those coordinates as seen from the Millennium Falcon. The Falcon is traveling with a beta of 0.6, so that means that their gamma is 1.25. So let me write Lorentz equations. So in order to find the time, I will substitute it here. Gamma is that 1.25, TD is 8 seconds, minus, this is V over C, which is beta. So this thing here is V over C and position over C. So beta is that 0.6 and X over C is that 3. We substitute that and we get that this is 7.75 seconds. So it takes place at 7.75 seconds as seen from the Millennium Falcon, which is what we found by using Minkowski spacetime diagrams. Now let's find the coordinates as measured by Kessel of that explosion of the meteor on their shields. So these are the coordinates as seen from the Millennium Falcon. They have the prime. So in order to go back, I have to write now that xq is equals to gamma x prime q plus vt prime q. Now I will divide everything by c, so this will be x q over c, the speed of light gamma x prime q over c plus beta t prime q. Then I can use those units. Now gamma 1.25, q prime over c 2 seconds plus beta 0.6, t prime 3 seconds. That gives us a position of 4.75 seconds, which agrees with what we found on the diagram. Now, in order to find the time, I move this here, and this is T of Q is gamma T prime of Q plus V over C times X prime Q over C. Again, 1.25 T prime 3 plus beta 0.6 times X prime 2 seconds. This gives us, if you use your calculator, a time of 5.25 seconds, with it is what we found using space-time diagram, Minkowski diagrams. So you can use the equations, Lorentz transformation equations, and you can use the space-time diagrams, Minkowski diagrams, if they are well calibrated, to get the exact same result. So science works, relativity works. May the science be with you.